So let's now look at the binomial distribution. Yesterday we talked about binomial probability. Now, binomial distribution is when you do several Bernoulli trials, and each one of those would have a binomial probability. So X will represent the random variable denoting the number of successes in these Bernoulli trials. But what we saw yesterday, the probability of that would be, well, NCX, p to the power of x, the probability of it happening to the power of x, probability of not happening to n minus x. So p is the probability of success, same as we saw yesterday. X is the number of successes that we have, and n is the number of times we repeat the trial. So if I was now to put that into our frequency table, not quite as simple as our other ones, because of course we don't know how many terms we've got, so we'll go up to n. I know from the binomial theorem all of those will add up to be 1, so that's all our probabilities. The best I can say for the sum of the xpx row is that it's the sum of all of those terms, and similar with the x squared px. Let's work out the expected value of x then. So it'll be the sum of all those terms. I'm going to play around with this. If I pull out the very first term, which is when k equals 0, and of course that very first term that I pulled out would equal 0, because it's going to be 0 times that. I'm now left with the sum from 1 to n. I'm going to play around with that. If you think about these NCKs, I'm going from 1 to n. So I'm going to have NC1, NC2, NC3, all the way up to NCN. Now, the formula for NCK, remember, is n factorial on k factorial n minus k factorial. So every one of those NCKs would have a common factor of n. So I've pulled out the common factor. But it now becomes times n minus 1c k minus 1. Now, n is just a constant value. So I've pulled the n out to the front of the sum, because every term is going to be times n. But the other thing I pulled out is p, because every term is going to have p to the power of whatever k is. So each term will have p to the power of something. So I'm going to pull the p out as well. So I now have np, k equals 1 to n, of n minus 1c k minus 1, p to the k minus 1, q to the n minus k. Now if you look at those two powers, they add up to give n minus 1. So I could rewrite that sum. Instead of going from 1 to n, I could say I'm going from 0 to n minus 1. It will give me the exact same sum. But notice I've changed the k minus 1 to k. So in this one, the first time I subbed in, I would have subbed in k equals 1. So I would have got 1 minus 1, which is 0. The second one, I sub in 0, I get k is 0. So I'm still getting the same number. Now if we look at the powers, the same thing happens. In this line, k equals 1, p would be to the power of 0, q would be to the power of n minus 1. On the next line, k equals 0, so p will be to the power of 0, q will be to the power of n minus 1. It's still the same sum, I've just changed what the term looks like. So a little bit of maths magic there. That's our binomial theorem for q plus p to the power of n minus 1. But remember, we know p plus q is equal to 1, because it's all the probabilities. So that's just 1 to the power of n minus 1, which is 1, and we get np. So our expected value is np. Now think about what we saw yesterday. Remember the expected value with our Bernoulli. It was p. We're now doing n trials. So we're expecting for every one of those trials to get p. Well, if there's n of them, then the total would be n times p. So that's I guess a simplistic way of doing it, but there's a proof if you like. Wow, strap yourself in for this one. Now we're going to do the variance, which you'll recall, expected value of x squared minus the average squared. I'm just going to play around with the x squared a bit. So if you thought I did a bit of maths magic before, watch out on this one. So x squared I've rewritten as x times x minus 1 plus x. If you play around with that, sure enough you get x squared. The mu we've already worked out, we just said that was np. So square that, we get n squared p squared. Okay, let's go back to the expected value. I'm going to split that up into two things. The expected value of x times x minus 1 plus the expected value of x, which we worked out was np. So I've substituted in np for the expected value of x. Now I've got to work out this expected value of x times x minus 1. All right. Well, by our definition of expected value, that would be k times k minus 1, nck, p to the power of k, q to the power of n minus k. I'm going to take out the first two terms this time. And both of those turn out to be 0. So when you substitute in 0, substitute in 1, you get 0. That now leaves me with this sum, which I'm now going to play around with. Similar to what I did before, that nck factorial, every term in that sum would have an n and an n minus 1 in it as a common factor. So I've pulled out the n minus 1. It would leave me with n minus 2 ck minus 2. Okay? P to the power of k, q to the power of n minus k is still the same at this stage. Well, n's a constant, I can pull that out. N minus 1's a constant, I can pull that out. I'm also going to pull out p squared, which means my p inside the sum becomes p to the power of k minus 2. So I now got k equals 2 to n of n minus 2, k minus 2, p to the k minus 2, q to the n minus k. Well, I can rewrite that sum as k equals 0 to n minus 2 of n minus 2 ck, p to the k, q n minus k minus 2. Again, if you look at those two powers, they add up to give n minus 2. So in fact, we have p plus q to the power of n minus 2, which is 1. And we end up with n minus 1 p squared. Now remember, that's not the answer we're looking for. That was just working out e, the expected value of x minus 1. Let's go back to our variance, which was the expected value of x minus 1 plus np minus n squared p squared. Sub in what we just worked out. Now we just play around with the algebra. We get npq. Again, think about yesterday. When we were just looking at Bernoulli's, we said the variance was p times 1 minus p, which is q. So pq, we're doing n of these, so we get npq. What can we quote? Again, as I say, highly unlikely they're going to ask us to go through and prove that. But if x is binomial, and this time the two pieces of information we need to know is how many times are we repeating it, so that's the n, and p, what's the probability of success, they're the two bits we need to know, then the expected value would be np, and the variance would be np 1 minus p. If p is less than half, the distribution will end up being a positive skewed. If p is equal to half, you'll get a nice symmetric distribution, and if p is greater than half, you'll get a negative skewed distribution. Remember yesterday when I said with that Bernoulli one, oh, they're not on the reference sheet? You just need to know them. They are hidden on the reference sheet because this is on the reference sheet. So a Bernoulli trial would be a binomial where the number of trials is 1. So therefore, we can say, oh, well then the expected value of a Bernoulli trial would be 1 times p, which is p, and the variance would be 1 times p, 1 minus p. So it is on there, but it's hidden. Let's have a look. State whether a binomial distribution could be used in each of these problems. So in other words, is it a binomial distribution? Could we model it that way? We've got a dice, we're going to roll it 10 times. We want to find the probability of getting 3 4s, 4 5s, and 3 6s. So no, that one would not be binomial, because we're interested in 3 different outcomes here. We want, on some of the rolls we want to get 4s, some of the rolls we want to get 5s, some of the rolls we want to get 6s. So that's not a binomial distribution. We're repeating and we want the same outcome for it's either going to happen or it's not going to happen. If we had said we want to find the probability of 3 4s, that would be binomial, because we're interested in how many 4s are we going to get, or 4 5s, or just 3 6s. But when we're saying all 3 of them, no good, because it's 3 different things that we're interested in there. We're going to toss a coin, and we're going to keep tossing it until a head occurs. And we want to find the probability that we end up with tossing 8 times. Well, again, that one won't be binomial, because we need to know the number of outcomes, how many times we're repeating the trial. In this case, we don't know how many times we're repeating it. So that would not be a binomial distribution. So the random variable here is actually the number of tosses, not whether it's heads or tails. A jar's got 49 balls in it. 6 of the balls are selected at random. Probability that 4 of the 6 have an even number. This is interesting because actually it might be and it might not be. It all depends. Are you replacing the ball each time or are you not replacing the ball each time? If you're not replacing, then it's not binomial. Remember, the probability has to be the same every single time. So if you don't replace it, it can't be a binomial distribution. But if they do replace it, then it would be a binomial distribution, because the probability would be the same every single time. So in fact, we could say, yes, that is a binomial distribution. The number of trials we're doing is 6, because 6 balls are being selected, and the probability of success, well, there's 24 even numbers from 1 to 49, so 24 out of 49. And the actual probability, there it is. Well, unsimplified. Turns out, I'm not going to worry about trying to write that as a fraction, the numbers are just too big. But 0.2247 would be the probability. So we're doing a binomial. We've got our distribution table drawn up there. The question is, what is the probability of success for one trial? So the Bernoulli, if you like. What is that one? Well, I can pick any one of those to use. I'm going to make life easier for myself. I know it's binomially distributed. Number of times we're doing it is 3. The probability is p. That's what we're trying to work out. What is the probability? I'm going to use x equals 3. So we're saying the probability that x equals 3, 0.027. Well, x equals 3 would be 3c3. Probability of it happening to the power of 3. Probability of it not happening to the power of 0. So we're just saying, well, p cubed then must be 0.027. So the probability of success must be 0.3 for that particular experiment. So now we could work out the variance. The variance we said was NP 1 minus P. So N is 3, we're doing it 3 times. We just worked out the probability of success is 0.3. And so therefore the probability of failure is 0.7. We end up with 0.63 for the variance of that distribution. 3 distributions. Which one is which? No cheating. No cheating. Well, I think it's fair to say A would be the symmetric one. But the question is, which one is the positive skew and which one is the negative skew? Which way round does it go? It's always backwards to what I think it should be. Because negative skew has them all bunched up further to the right, and positive skew has them bunched up to the left. In my head, it should be the other way around, but it's not. That is the correct way of doing it. Which distribution is most likely to have an individual trial with a probability of greater than whatever pi on 5 works out to be? So I guess the key here is pi on 5 greater than a half or is it less than a half? Okay, who's worked it out? Okay, so if the probability is greater than half, which one is it more likely to occur in? The negatively skewed one. Because look, here's the distribution. More of them are over here. So there's a greater chance we'd end up with a probability of pi on 5. What did pi on 5 work out to be, by the way? 0.6. 0.6. Here's our random variable. It's a binomial distribution. We're repeating the trial 150 times. Probability of success is 2/5. Let's find the mean and the standard deviation of this distribution. Okay. The mean we said was n times p. So we get 60. the variance, not the deviation, but the variance is NP 1 minus P. That works out to be 36. Deviation is the square root of variance. So we know that the standard deviation would be 6 for that one. How many more trials would be needed to increase that average to 100? So we now want NP to equal 100. So N is 250. And that's 100 more trials. What effect would that have on the standard deviation and the distribution itself? Well, the standard deviation, variance now becomes 60. So the deviation is 7.75. It was 6. And deviation measures the spread from the average. So we're now saying it's got a bigger spread. So it would be more spread out. So the data would move further away from the average because of the bigger deviation. We've got an experiment. We're going to roll 2 dice and we're going to roll them 10 times. And the number of times the total turns out to be 7 is what we're interested in. To find the mean and the standard deviation. So X is going to represent the number of times that total is 7. It's binomially distributed. We're doing it 10 times. The probability of success would be, well, 6 in 36, which is 1 on 6. So our average is N times P, 1.67. And variance is 1.3889. So deviation 1.18. Now, these are the more likely type of questions. As I say, don't panic about that derivation that I did earlier. That was just me having fun. Now, this experiment is simulated 1,000 times, and the results are recorded here. So 193 times, no 7s turned up. Sorry, no times did 10 of them turn up, get it the right way around. So find the mean and standard deviation of that simulation. Now, the mean will be the expected value, which is the sum of X, whoops, let's go back to it, X times frequency, or relative frequency. X times relative frequency. So 1.633. Let's work out the variance. Expected value of X squared, so that would be our X squared times the relative frequency, minus that mean we just found squared. But we want deviation, so it's the square root of that, 1.22. Draw both of the polygons on the same set of axes. Okay, the blue one is the simulation we just did. The orange one is the theoretical probabilities. You can see, repeating it 1,000 times, it's not that far off the theoretical. Remember, in probability, the more times you do it, the closer and closer your experimental comes to be theoretical. So that's, yeah, that wasn't a bad match. All right, 17B.